Okay, so today we're going to talk about one size doesn't fit all, make a case for federated data science. By the way, just to show of hands, how many data scientists in the house? At least one. So sir, keep us honest, because none of us are data scientists, at least by training, so maybe a little bit here and there. So my colleague Suhas, who spends most of his time on the customer side, and there are three names here. Those three are like special mentions. Those are our three interns who actually worked on most of the Python and R integration over the summer. So kind of a shout out to those guys. So we'll start out with pretty much the same message that I think Russ started, slightly different conclusion. You do see that data scientist has a lot of tools to deal with, right? I mean, everyone has their own sort of favorite tool. In fact, if somebody claims that I'm not a data scientist, chances are at least you have used Excel. And you see that common across all the board. You know, you talk to any scientist in terms of crisis, you can say, okay, R snapshot CSV, put it in Excel, send a chart, put it on PowerPoint and send it out. Very, very common, right? So you're not alone there. So, like I said, a lot of choices to pick from. But I think we're going to a slightly different conclusion. But data processing also is an iterative multi-step process. You know, you look at, you're going to kind of get me the golden data set or any data set for that matter. You try and flatten it, try and extract models, feature sets. That's kind of iterative by design. And eventually you'll get to a point where you say, okay, I'll either deploy my model in production or I do something with it. Probably start feeding something which is more real than my little science experiment on the side, right? So I think a very simple question is, this does reduce your sort of increase your time between when the data stream is captured to when some of the intelligence is extracted out of it. What about if we just put in essentially a fast object access across stages, right? So instead of going through this file system, you sort of keep a mutable copy or an object representation of data in memory, and then try and at the end when you're sort of ready to sort of send it to posterity or for compliance reasons, set it out in one shot. So kind of keep an active tier in memory. That's pretty much what Ampool is. So I'll probably spend maybe 4 or 5 minutes on Ampool and what we do, so that you have a good sense, and we'll go too deep into some of the, I would say, the specifics around what the kind of experiments we have done. So I think, as I said, the benefit of this approach is to actually reduce time to insight. So the delay between when the data is captured somewhere in the organization to when let's say data scientists even get a hand on it. That's the time where a lot of value potentially is lost. I think some of the advantages of this approach over some of the traditional file-based system is the data exchange is kind of object-based in memory, so you're kind of cutting down that time. You're trying to reduce the data copies. Remember that busy chart for 4 Dexters and a lot of golden data set variants? I mean, you're trying to avoid and minimize it as much as possible. And they're kind of giving you that end-to-end speed up, right, in those scenarios. And also the concurrency, right? Because if your data is in memory and assuming it's highly performant, then you can have multiple tenants trying to access that data and do wonders with it, right? Multiple data scientists for that matter. So Ampool is a memory-oriented active data store. We talked about it. I think it's kind of powered by one of the projects. So if you've heard of the product called Gemfire, so it's kind of a variant. So Gemfire was contributed in open source last year by Pivotal, and so that's our kind of building block for distributed store. We didn't want to invent the wheel there. The other thing, what it does is that you kind of, instead of acting as a cache, it essentially becomes an active primary storage for all active data, right? And then the intent is that you store all that data and then update it as required. So kind of not have the immutability. But you see in analytics is people take snapshots because they cannot or they don't want to make changes to the data. And in this case, we do allow at least the early stages for the data during ingest and ETL to actually make changes to it. And then the value being that you're trying to serve the data concurrently to multiple stages, right? Question.
What does memory oriented mean?
So memory oriented question is what does
in memory or
memory oriented means? Yes. So in memory is the DRAM is one of the layers, but there are other layers. Like you're talking of storage class memory, some of the 3D X-point work and the innovation that's coming up, as well as SSDs, right? So different flavors of memory and acting as different data tiers, and we sort of manage tiering of data across. I think there's probably a couple of slides later on that'll make it. So I think one of the other fundamental design decisions we made was we kind of stayed away from integrating compute, whether it's frameworks or languages or tools, inside the in-memory layer as much as possible. So as a result, we focused on just the data representation in memory. We have a few variants. We inherited key value store from Geode, and then we have added a few table variants. One for essentially your dimension table, so kind of very easy to update that data and make changes to it. And then the other ones is more like the fact tables, or like think of IoT worlds as a fast incoming ingestion of data. And then all you do is typically just append the data and just keep creating that and growing that with time. So some of the integrations, Spark and Hive for obvious reasons. And then also there are some other engines. Trafodian is again an Apache project, kind of essentially an ANSI SQL compliant operational SQL engine working on top. Data torrent for even fast ingestion, kind of streaming analytics, as well as CDAP. I think you mentioned, right? You saw what CDAP does, so I think we have integration there as well. Similarly, on the south side, we have kept the layer pluggable, where the idea is to move data whenever you are ready to sort of send that data to warm/cold storage, that you sort of send that over, right? It's kind of the idea is, we intentionally wanted to stay away from designing yet another tool chain. There are plenty already, right? So the idea is that we wanted to, make minimal changes in application logic. The only change you make is where you fetch data and where you send that data back. Similarly, no changes in user tools. So you can get memory speeds without having to say, oh, here is another window of your data, and you can try and access it from there. And then also trying to keep the deployment hassles away, right? We don't want to create, oh, here's another monitoring and management UI. You kind of use your existing ones, and we have plugins to actually operate on the data. So that's kind of describes, this is kind of the, it gets into the gory details. So we inherited a bunch of functionality from the Apache Geode project around low latency communications, kind of essentially a key value store, because that's very common for, let's say, an application cache, right? And what we did was we added a bunch of capabilities around it so that it becomes more meaningful for operational use cases or in terms of data access. And then we have APIs in both north and south layers, so if you don't find a plugin, you can start building your own, right? I mean, at least that's the whole idea. So let's get to sort of the meat of the problem. I mean, anomaly detection is just one of the, you can probably pick any other use case as well. Basically, what you have is, now it's not hard, so it's still chipped in. Think of this as essentially a flow where a bunch of cardholders, right there. I'm using a fraud detection in a more financial transactional use case, or at least in that context. What you have is that you have, a bunch of people making credit card transactions, or well, at the end of the month, hopefully they're paying their bills as well, because that's what they do. You look at merchants; they kind of, obviously offer their scanners, and transaction travels from there. There's probably anywhere between 2 to 5 different intermediaries before it literally gets to the issuer bank, right? So we are not going to talk too much about those sort of middlemen, for lack of a better word. It's pretty complicated. I've seen, if you literally Google for credit card transaction workflows, you'll probably find 15 other. I mean, there are so many variants, right? So it's pretty complicated. I would say this is almost a very simplified model of how the data flows from one end to the other. So we're going to focus on essentially once the transaction logs get to the bank, and they have sometimes very split seconds to make calls whether this is a legit transaction or not, right? How does the data scientist there even look at transactions, or how the models sort of behave? So kind of double clicking on those two aspects. What we have is that we took essentially those transactions. There's also, let's say, there's a rep or whoever is monitoring some of this, and you can also have these capabilities exposed directly to end users as well, right? So they would be taking charge of their own transactions, acknowledging whether that's legit or not. So some of those workflows around validation of transactions called cross-validation, I mean, that is going in the system as well, alongside transactions. And then you essentially, like at a higher level, 3-step process, right? You ingest the data, you do streaming or batch processing. We chose Spark, but you can, I mean, some of that, whatever is there in process, could be anything existing, or whether it's legacy or something that's new and upcoming. But then you can arguably have data scientists coming in with their own tool chain, right? Say, okay, I'm comfortable with Python, my models are in Python, I'm not rewriting a lot of them. For those use cases, you do need to expose that data as it's happening to some of those other stakeholders as well. So that's kind of at a higher level, right? Is sort of how the data is flowing in the system. There's a question.
So if you did not have exploring model and the sequence was ingest with Spark processing, what is the additional capability that Ampool will bring to the table?
So I think this is literally one of the configurations, since we have plenty. So for instance, I could plug out Spark streaming or Spark for instance, and replace it with data torrent, for instance. In fact, earlier this year, we actually did an AdTech use case, which exactly had very similar data flow, but you can, the only difference was instead of using Spark streaming, using data torrents. Likewise, there are scenarios where we can have, if you don't want the delay anywhere, you could choose to, there are APIs available, you can choose to ingest data directly in the layer as well.
More specifically, if I focus on streaming ingest in Spark, do you see an acceleration over tachyon-based load and store as opposed to Ampool? Have you seen an acceleration there?
Yes, so the question is, instead of using Ampool, if in that same ingestion route there was tachyon, have you seen it? Yeah, so I think we have done some comparisons, not an exhaustive one, because what happens is, depending on the data sizes and the complexity of the flows, you have sort of different mileage, right? Mileage may vary. But at least when, let's say, the scan read, just a reading, instead of incurring that file system protocol translation penalty on a, let's say, a pure read, we were like seeing about 5-6x compared to tachyon. Again, those are very, very atomic operations, so I sort of always give that words of caution, right? Don't read too much into it. I think, so for instance, if your end-to-end pipeline is 80% compute, some of that delta may not even matter to you. Or else, if you have delays artificially, I mean, IoT use cases, sometimes you get a drop from one of the installs, let's say once a day. There goes all your, all your bets for real timeless, right? So I think it's just reality of things.
So just to bottom line that what you're saying is somewhere at certain points in time, if you have laggards in your processes and so on and so forth, that is where Ampool is able to make a very significant difference, or if you're operating on the same data sets, maybe different.
Right.
And if you have an IO problem, that is where you will start to see.
Yeah, I mean, I think you have to, at some point, take a 10,000-foot view and say, oh, where are your system delays, and you can address part of the problem. So I think my last slide, this again gets even further down. So people saying, okay, where is my data and how is it stored internally? So I'll just quickly walk through, because a lot of this would be essentially be seen firsthand when Suhas shows the demo. So kind of similar data flow, but now what we have is we are doing financial transaction logs, and then some of those user and app data changes are going straight into the Ampool there. Through that Kafka stream, you're kind of creating from RDDB stream and then converting to data frame and sending it over into essentially 2 different tables. You see the different colors because one is more like an append-centric fact table where you'll get a lot of those transactions and they keep on adding. You typically don't go back and change a transaction. It is what it is, right? And then outliers is something that you could, you update it, but then based on if cross-validation happens, saying that no, this is a legit transaction, you probably go back and update it as well. And then model is also something that you can serve from the memory layer as well. You can have multiple models stored too. So if you wanted to, for instance, extend the slide and add, let's say, a Python block or even a, some other batch processing, let's say a Hive block, you can actually do that. And all of those could still have a role to play in this overall decision-making process. So, any questions before maybe Suhas?
Yeah, so I think while you are still on the slide, just want to quickly mention a few things about this demo. So I'm going to demo this scenario. where we have simulated, we don't have a real transaction, financial transaction, but we have simulated basically a transaction generator, and we have chosen actually two features. One is the distance of your registered location, of your transaction from the registered location. I mean, where have you made the transaction, where you actually live in Campbell or Cupertino and so on, versus what is the amount of transaction. And based on that, we have used basically the computational model or analytical model to really find out which transactions actually fall within a given variance as well as the mean of a range of transactions that we typically do, right? So we do calculate, as we get these transactions, we actually use Spark batch job to really calculate the model. And we also use this cross-validation data, which essentially means it's feedback from the person who actually really validates whether this transaction was really fraud or it was just false positive, right? So based on that, this model uses both transaction log and cross-validation data and basically comes up with a model. And essentially that model is run in this Spark streaming pipeline as newer transactions come in, and essentially find out if any of the transactions are sort of outliers. Now, the interesting thing is, like, we have all this data in memory, so actually the access to data is very fast, and essentially this whole building of the new models can be done at more higher frequency rather than actually collecting all the outliers. And you can think of the credit card transaction as soon as it happens. Many times you get the call next day, right? Asking by the bank person whether the transaction you did is valid or not. How about, you instantaneously get a notification on your cell phone app saying that, oh, you did this transaction, seems to be odd. Can you please confirm whether this transaction is correct or not? So that way the amount of feedback through cross-validation that you get as well as the transactions, there's a lot of data coming in. And for analyzing that data, actually, you have to really be in memory. So that's where the value of Ampool really plays in.
So the batch process that you talk in Spark, right? I was under the impression that you take a first time load there to get everything in memory, and then the catalyzed optimizer, which is there, builds the plan. You're no longer hitting back into the memory down. So it's a one-time cost. Is it correct?
No, so batch processing is actually you want to do it periodically to optimize the model, because the transactions, your pattern of transactions is changing over the period of time, right? So last basically a few days, whatever the transactions you did, right? And based on that, actually the particular model was built for a user. But now that model needs to be optimized again for the next or over the last few days worth of data, and generate that model to basically analyze your next set of transactions.
No, that I understood, but the memory that you have for the Spark engine as such is competing with the Ampool memory. I'm saying that one-time cost, once you pay, then everything is in memory for Spark, and you may not even fit Ampool.
No, so see, the thing is, like, even with the Spark, right? For example, Spark streaming and Spark jobs. So even with the Spark, you may not have a single job. So between the multiple Spark jobs, again you would spill the data, right? Where would you spill the data? You want to spill the data on the disk, or you want to spill the data in an in-memory store? So that's a value. So definitely, you load the data once, right?
But
that's not typically the case.
If that memory that you're competing with Ampool to Spark, then you don't have the problem, because I'm saying it's memory.
Of course, but think of it this way, right? Your computational framework, which is Spark, which is loading the data once, right? But it many times actually data is not going to fit in. So it actually, whenever it creates more RDDs, it has to basically go and spill the data, right? Now this memory is not only DRAM, but Ampool also considers basically the NVDIMMs, the storage class memories, and SSD, and give you the seamless extended memory sort of this thing, right? So that's where the Spark memory versus the Ampool. Ampool is still basically a in-memory data store, versus Spark is just caching some data for temporary processing, whatever is required in that job. Make sense? Yep.
So is it like ample memory versus not so ample memory?
That's perfect.
I have a question.
Yeah.
So, continuing this gentleman here asked the question about Aluxio versus what you do. So, I know Aluxio does or API. It's a file system like API. What is the concept that you provide to access Ampool?
So we have a Java APIs. Essentially, it's an object store API. So we do more like H-based kind of APIs. You do get put stuff, and we also have scan. So we have two types of tables primarily supported in Ampool. So one is sort of a fact table where the kind of workload is a fast ingestion and keep on appending the records as fast as possible. Versus another type of table in memory is essentially a mutable table where you actually need more of a transactional kind of a workload where insert updates has to be done very fast, right? So both these kinds of tables are required because typically the mutable tables are used as a dimension tables, and these continuously growing with streaming data kind of tables are used like a flow tables and that's where you actually most of the time these kind of tables only require scan. You don't need to really do a get put updates on those tables. So we support both these abstractions, and we support the get put and scan APIs through Java.
And do you have transactions which can update several things and then either atomically succeed or fail?
No, so transactions actually come on top. So we actually are partnering with, so as Nitin explained, right? So we focus on in-memory data store versus the computational layer on top. Like for example, you can have a Spark, you can have a Hive, or you can have a full-fledged SQL engine on top of this, which is making use of this thing. So we are working with Trafodian, actually, which is a SQL engine that gives you more of a transactional capabilities, which underneath uses the in-memory Ampool data store for storing the data. So Ampool as such doesn't deal with the transactions.
In the interest of time, let's just get with the demo, and I think we will take 2 questions at the end.
So quickly, this is the directory where I've installed the Ampool. So I'll first make sure. Yeah, so I'll basically start. So Ampool actually has a command line shell that you can use to actually do create the tables, view the metadata about the tables, start, stop the Ampool servers on your cluster, right? So actually, so I have already started. Stop the servers because I closed my laptop. So Ampool actually has 2 types of server. One is locator and one is an actual cache server. So cache server basically manages your memory on individual machine, versus locator is, you can think of like an edge-based master, which effectively redirects clients to a less loaded server, so that client can fetch the data or put the data into the server. So let me actually first stop this system. I think when I shut off my laptop, give me 1 second actually. So meantime, maybe actually you guys can just get going with some additional questions you may have. I'll just quickly make sure that I have corrected this problem.
Any more questions?
The Geode website says that they support transactions and you said that you don't.
So we are not using Geode mechanism for transactions. That's what it means. So we didn't want to overload the
transactions versus distributed transactions. We support local transactions, we don't support distributed transactions from Geode. We probably haven't tested them. Jax can fix that.
quick question, which is, and I'm embarrassed for mentioning a competitor, but how do you compare to HANA in terms of functionality from SAP, which is also an in-memory database?
So we haven't had a direct comparison with HANA yet. I mean, HANA has been obviously around for a lot longer. But I think the fundamental distinction is that
you're probably way cheaper, number one.
Yeah, I mean, so
that's what I'd say. But I'm just saying, in terms of placing the technology,
right,
you would fall into the same category.
So HANA, I think, so just to for full sort of, I would say, apples to apples comparison, it's mostly HANA Vora versus the actual HANA, because traditional HANA goes more in, not in the typical like either big data or sort of open deployments. It's mostly enterprise or
it's working off SAP.
Right. It's getting
but
more
ignoring the integration with SAP. Is your functionality somewhat similar?
Yeah, it's similar, but the delta would be we don't want to embed compute. So all the vertically integrated stacks, like HANA, you could even argue MemSQL is just a SQL solution. What we're doing is we are sort of solving it horizontally, saying, okay, let's solve the data serving problem from memory fast and efficient, and let people choose their own compute engines. And that's the biggest distinction.
I see, okay.
And it's more philosophical one, but then the big question would be, is some of the parts equal or better than the whole? And at that time, I think it's, like I said, managed by very depending on what you do.
Very helpful.
Is that like you're cutting it at storage engine?
Right, so it's actually lower than that. So we are sort of literally serving it as so a SQL layer plus Ampool will essentially become your equivalent SAP HANA.
So the other question I have is that in many of these key store systems, you don't actually put the whole data into memory in order to maximize the amount of data that you can pool. Are you actually doing the raw data, or are you just putting a key data link to it?
No. So we are, at least the idea is to ingest all sort of the hot or active data in memory, not just the references.
Not a key data storage in memory.
Right. So what we do have though is for especially the tables like those fact tables or those tables where there's a lot of data and you kind of cannot plan for it because ultimately the tank will fill up. At that time we start doing the tiering. And that's when, say, okay, 2-week-old data can tier.
Is your second tier SSD?
Second tier can be storage class memory, which is NVDIMMs or 3D Xpoint. In fact, we've worked with one of the partners who showed we were getting about 22x compared to writing directly to, let's say, a file system or even like a HDD kind of based solution. So again, it's not getting into the IOPS thing. The whole idea is kind of create that horizontal layer where you bring your compute. We don't want to overcomplicate our lives and your lives by maintaining multiple versions.
Got it.
So quickly going over the flow of the fraud detection use case. So actually we are basically using some seed files to really load the data, transaction data and the cross-validation data using the Spark batch job. So this is the one which actually loads the data into Ampool. So this program essentially is a Spark program, and I will quickly show how easy it is to load the data using the Spark data frame and Ampool. So all we are doing is basically we are reading the seed data from these two files, and then essentially we are so we are essentially creating the Spark context. We are reading those files into Spark data frames, and the way to write these data frames into Ampool tables is automatically these data frames, the schema and everything will be discovered, and you will get the in-memory tables created in Ampool. So all you are doing essentially you are specifying where the Ampool's locator host is and the port is, and you are essentially saving these two data frames. One is the cross-validation data and one is the transaction data into Ampool. And that's where this model would be now generated based on the data stored in Ampool by the next program. So we can quickly check in Ampool. Now you have basically these two tables get created, which are actually showing the data. So it basically gives you some idea about the 500 cross-validation records are being populated in this database. So the next one is essentially we want to generate now the model. So I already have the model file which was generated in the /10, so I just deleted one, and now I'm going to essentially load, generate the model, batch model program. I'm going to load it. So this is a generate model program which will essentially run over the training data set and generate the model using the Spark batch processing. And the actual model right now we are storing it in the file system, but it actually will be stored in menu. So this file in the /10/model.txt will essentially catch the mean variances and the actual probability epsilon to find out when the next event, when it comes to the Spark streaming, when to categorize it's an outlier or it's not an outlier. So at the end of this program, it also basically makes sure that it has worked properly, it finds out some outliers in the existing data set that it's known about. So what I will do is now I will run this Spark streaming program. So this is the Spark. So this is the Spark streaming program. Now it will continuously run in the background, and its output will basically go into /10/run.out, and that's where it will basically keep on spitting out how many transactions it basically received. Because it's a Spark streaming, it's a D stream, basically where it's a bunch of, it's a sequence of RDDs that we are getting. So we are waiting for every 10 seconds to get the new RDD, and on that RDD basically we receive multiple transaction events and we find the outliers from that. So output of this program will essentially tell you how many transactions you received and how many outliers were found through this anomaly detection stuff. So this program is running. So I'll keep it running in the background. And what I'll do is basically I'll just insert a quick transaction data, which is a simulated data. So I will just run it, and this is essentially inserting for a given user. It's inserting lots of transactions into the system. So it's inserting them into Kafka, and the Spark streaming program, which is running in the background, is picking it up from the Kafka and analyzing it. So I'll probably keep it running in the background, and what I will do is you see actually the streaming program is waiting 10 seconds and going through. I think to get more relevant output, I think I'll wait for number, just to show you that how many transactions we are receiving. And so this is the RDD number 13. So every 10 seconds you are getting new RDDs, like so many transactions you are receiving, and out of that so many transactions in a given RDD, you are actually finding so many outliers. And this information is essentially getting stored into Ampool, as we saw, as a transaction or transactions as well as the outliers. So we can very quickly check that. And right now, so you can see that outliers and transactions are the two tables got newly created, and essentially that. So you can see actually there are almost just within last minute, it got about 760,000 transactions were inserted, and now outliers were created. So I think at this point I'll stop it. There are a couple of other things we wanted to show, but I guess we are already running out of time. So
thank you. It's ugly, but it works. That's very
yes. Thank you.